Hi, this is Anshu, and in this session I'm going to discuss some basics of probability. During this session I will be covering the definition of probability, common terms that are used in probability just like mutual exclusive events, independent events, etc. Venn diagram, basic laws that apply on set theory, examples of probability, conditional probability, and a Bayes theorem. Starting with the definition of probability, a basic question that comes when we talk of probability is what is probability and in what cases do we use probability. So probability is nothing but a study of a randomness of occurrence of a phenomenon. For example, when we say that the phenomenon that is going to occur is not the occurrence of phenomena that is going to occur is not deterministic. That is, we cannot figure out with 100% confidence that at this point of time, at this junction, your phenomenon is going to occur. Then that is called as randomness. Or when we say that there is a chance in the occurrence of phenomena, the phenomena may occur or may not occur. It is we are not 100% sure that the phenomena is going to occur. Then to determine that randomness, we calculate probability. So it's just a study of the randomness of occurrence of a phenomenon. Now, what is called as a random experiment? So, whatever phenomenon that is going to occur will have some outcome. So this phenomenon, this is generally referred as a random experiment. So there will be some outcome of this random experiment. So that outcome generally lies in a sample space. Sample space. Sample space is nothing but a collection of all the possible outcomes that can occur when you perform a random experiment. For example, if you consider tossing of a coin as a random experiment, then in that case, what will be the sample space for tossing a coin? It will be head or tail. Because when you toss a coin, either you can get head or you can get a tail. Similarly, if you throw a dice, rolling of a dice, what will be the sample space? It will be 1, 2, 3, 4, 5, 6. So whatever possible outcomes that can come when you perform an experiment, that constitute a sample space. Okay. Sample space can be finite or infinite, can be discrete or continuous. So just like here you have a sample space containing head or tail or 1, 2, 3 to 6. So here you can count the number of outcomes. So this is called as a finite sample space, or you can say as a discrete sample space. But in random experiments where you have a involvement of time, or the experiments where you don't have a discrete sample space, that is you cannot count the possible outcomes, where you say just make a general statement that the outcome may lie from within a range of some numbers. Okay, then you say that the sample space is continuous because you are not able to count the outcomes. Okay, so that is called as continuous sample space, and this generally happens when you have involvement of time in performing an experiment. Okay, whatever experiment you are going to perform, it is called as an event. Okay, so if you have a head or tail, okay, so you had performed an experiment, then you got head or tail, and or rolling of a dice from you will get 1 to 6. So that way you have performed an event. This is an event. Similarly, when you perform an experiment, there you can perform it once, twice, thrice, so on. So if you perform an experiment once, that is called as a trial. So trial is nothing but performing an experiment once. That is called as trial. Or in other words, the basic definition of trial can be single performance of an event. Now, in probability, we define all these things with some notations. So, event is referred by E, sample space is referred by S, this is sample space. This is event. Then you have something as cardinality of A. Let A be an experiment. Okay. So modulus of A is called as cardinality of A. What is cardinality? It denotes the numbers of elements in set A. So whatever experiment we are performing, we just refer to it as a set, and then modulus of A is defined as a cardinality of A. There are some more points like mutually exclusive events. This is a term that we will use very frequently in entire probability section. Mutual exclusive. Okay. Consider you have two events, A and B. Okay. So when these two events are not dependent on each other, that means occurrence of A does not have any impact on the occurrence of B, then you say that the events are mutually exclusive. Or you can say that there is no common points between A and B. Generally what we say is A intersection B is equal to phi. If this is the true, then A and B are mutually exclusive events. Okay? A intersection B denotes the number of common sample points between A and B. Phi is called as null set, or you can consider as zero also, but generally in set theory or in probability we define null set as by phi. It does not contain any elements. No. Before going into further details of probability, I will discuss basic concepts of Venn diagram. This will be helpful in proving some of the probability axioms. Okay. Now, what is Venn diagram? Venn diagram is nothing but a diagrammatic representation of sets. If you want to draw a Venn diagram, you draw a rectangular box. This is referred to by S, that is the sample space. It will contain all the points, possible outcomes that can happen for a random experiment you are performing. And if you have say one event A, so draw a circle. This will denote an event. So now all the elements that are in A are represented by the green lines. Okay, so the outcome of an event will always be within sample space. So you can say that A, your event, is a subset of sample space, or sample space is a superset of A. The other thing is when you say A, you have another term called as complement, which is denoted by A dash or A bar, or sometimes you will find AC. What is this? So this is nothing but all the elements of a sample space which does not belong to A. So the black lines in this diagram denote A bar. This is A bar or complement of A. Similarly, if you have you have two sets A and B, so how you will denote A union B or A intersection B? So what is A intersection B? It is a number of elements that belong to both A and B. What is A union B? It is a sum total of a number of elements of A and B, provided you remove the common duplicate numbers. Okay. Now you draw a rectangular box. This is again referred to as by sample space. Yes. Okay. Now what is, you draw two circuits A and B. You have A, you have B. If the diagram is like this, that means you does not have any common elements between A and B. Where intersection B is phi, because the circles do not intersect to each other. So this represents a mutually exclusive events. That means A and B are mutually exclusive. But if in case there are some common elements between A and B. You draw the circles like this. So now in this you can see that the circles overlap each other, intersect each other. So this section denoted by graph, this refers to A intersection B. These are the common points. Now what is A union B? So all, if you say like this, blue lines, all the elements of A plus the elements of B that are not common, those are defined by A union B. So this is the basic denomination of Venn diagram. This we will use frequently in proving axioms of probability. So there are some basic mathematical rules that apply on set theory that I will discuss now. So one rule is like basic rules of set theory. Okay. So some of the basic rules that apply on set theory are commutative law. What is it? It is defined as if you have A union B is equal to B union A. If you reverse the sets, then again the equation remains the same. Similarly, if you have A intersection B is equal to B intersection A, this is commutative law. The other law is your distributive law. So how it is defined? It is in this distributive law you will consider three sets A, B, C. Now such that A union B intersection C. Sorry, A union B union C is equal to what will it be? You combine this, you open the bracket and take this union as common. So what it will become? A union B union A union C. Similarly, if you replace union by intersection, A intersection B intersection C, what it will become? A intersection B intersection A intersection C. This is called as a distributive law. The other is associative law. Again, in associative law we use three sets. How we will define it? Sorry, there was a mistake. Just now what I defined as a distributive law, it was not a distributive law, it was an associative law. Again I will repeat, it's A union B union C is equal to A union B union A union C, and A intersection B intersection C is equal to A intersection B intersection A intersection C. This just now I referred to as distributive law, but it's not a distributive law, it's an associative law. By mistake it's okay. Now I'll discuss the distributive law. In that you again consider three sets A, B, C, but you have a combination of union and intersection both. You have A union B intersection C. What it will become is you combine union with B and union with C. So it will be A union B intersection A union C. Similarly, if you interchange union and intersection signs, what you have A intersection B union C is equal to, what you will get is A intersection B union A intersection C. This is called as a distributive law. There are some more laws like complementation law, identity law, idempotent law, etc. So, what is identity law? If you use a set A with a null set, so for example A union phi, what it will be? Phi, there are no elements in phi. That is it's a null set. So you will get again A. Similarly, if you take an intersection of a set with a sample space S, what you will get? Again you will get A, because A is a subset of S and S is a superset of A. That means S already contains A. So A intersection S is all the elements of A that are common with S. So you will again get A. This is called as identity law. There is other thing called as a complementation law. So when you take use a complement of a set with itself, what you will get? A union A bar is equal to S, and A intersection A bar is equal to phi. Why? A bar is all the elements of that belong to S but does not belong to A. That is, it has all the elements that do not belong to A. So when you take a union of A and A bar, what you will get a total sample space. Similarly, when you take an intersection of A and A bar is all the elements which does not belong to A. So in this case, there are no common elements. So what you will get is phi, that is a null set. This is called as complementation law. The other is idempotent law, where you use a set itself. A union A is equal to A, and A intersection A is equal to A. This is called as idempotent law because you use the set itself. The other is domination law. In this, you use what you will do is you will take a union of set with a sample space. So you do A union S. What you will get? S. And A intersection phi is equal to phi. Because every set will have null set as one of its outcome. So A intersection phi is phi. And A union S is equal to S, because S already contains all the elements of A. So what union denotes is all the elements, sum of all the elements of A and S. That is, we have S. This is called as domination law. There is one more called as absorption law and De Morgan's law. What is absorption law? Absorption law is like if you take a combination of union and intersection with only two sets. For example, A union A intersection B. Here, what you are going to get? So, if you open it, A intersection B, so it has all the common elements of A and B. So, if you take a union of A union, the common elements of A intersection B, so this contains only the common elements, and A itself has all those common elements. So, union gives you the sum total. So, what you will get? A in itself. Similarly, if you take A intersection A union B, so again you will get set A itself. Why? A union B is sum total of all the elements of A and B. Now you take an intersection with A, so it has all the elements of A plus all the elements of B. And you are just trying to figure. So the common elements between this and this will be common, the elements of A. This is called as absorption law. Lastly is, and the most important is, your De Morgan's law. So what De Morgan's law says, you have two sets A and B, and you take a complement of A union B. A union B. So what it will be? It will be A complement intersection B complement. prove it by Venn diagram. You have A, you have B, A, B, you have union. So what union will have? It will have all these elements. Okay. What is A bar? So A bar will have blue lines suggest A bar. And what is B bar? So again, for B bar, you need this is B bar. So black lines denote B bar, blue lines denote A bar. So if you see what it is, A union B complement. The complement of this is A bar intersection B bar. So all the common elements of A bar and B bar denotes. So all these rules can be proved using Venn diagram. And the other one is with intersection. So if you say A intersection B complement, so what it is? It will be the union of the complements, A bar union B bar. This again can be proved using Venn diagram. These two were the De Morgan's law. So I'll state once again: A union B का complement is equal to A complement intersection B complement, and A complement of A intersection B, what you will get is A complement union B complement. So this is referred to as De Morgan's law. There are few basic notations, like if you take a complement of a complement, what you will get? A set itself. You have A complement, then again you take a complement, what you will get? A. And if you take A union A bar intersection B, so what you will get? You will get nothing but A union B. Again, this can be proved using your Venn diagram. I'll write once again. A union A bar intersection B. This can be proved using Venn diagram. The other thing is, these were the laws. Now I will discuss the axioms of probability. So in probability you have three axioms. Those are the three basic rules